Afternoon, dear colleagues. I would like, first of all, thank all organizers for the possibility to present our results. And I see that my talk is the last talk before the meeting of the awarding committee, and I will try to present our results as brief as it's possible. I would like to tell about the magnetic properties of lithium vanadate, and all ESA measurements were performed in our institute, in Kazan Zavoysky Physical Technical Institute. Also, I would like to thank our colleagues from Kazan Federal University for magnetization measurements. And sample preparation was performed in two different institutes. First type of composites with carbon was synthesized in National University of Singapore, and the second type of composites with lithium phosphate was synthesized in Yekaterinburg in the Institute of the Solid State Chemistry. And then short outline, I will start from the motivation of our work, then some words about research objects, then magnetization measurements and how they can be connected with electrochemical measurements. And of course, the main part will be about the ESA measurements and then some conclusions. So, okay. You know that the search of the alternative energy source is a very popular topic right now. And of course, in our institute, it's also a very popular theme, topic, or investigations during maybe last 10 or 15 years. But I think that we have got very nice results during last 2 years in the field of investigation of materials which can potentially used for anode or cathode materials for lithium-ion batteries. And for example, like cathode materials, I mean lithium vanadium phosphate, they can be discussed in the frame of this conference because they have very nice magnetic properties. So both composites have granular structure, you can see here on the left side, but composites with carbon have the size of granules of composites with carbon much less. But at the same time, the crystal structure for both composites is almost the same. The crystal structure is monoclinic and lattice parameters are practically coincide. So then we started from the magnetization measurements, integral magnetic characteristic, and here you can see that the temperature dependence of magnetization for these compounds are not coincide to each other. So it's normal because the chemical composition is different for these compounds. But what is interesting? It's interesting that if we try to fit high temperature data using the Curie-Weiss law, we will see that Weiss temperature is much higher in absolute value. I mean, it's much higher for the compound with lithium phosphate. We suggest that it means the presence of short-range magnetic correlations in this compound. To prove this suggestion, we performed additional measurements of magnetization in two different regimes, field cooling and zero field cooling regimes. And we see the splitting here in the left. We see, one can see the splitting between two types of curves only in one sample, only in the composite with lithium phosphate, which as I have already told, which have the higher value of Weiss constant. And we suggest that this magnetic inhomogeneity can influence to the electrochemical properties. For example, the electrochemical measurements were performed for composite with carbon, and each has rather high value of electrical capacity. Unfortunately, experiments for another composite are not finished yet because we have some troubles, not with the sample, but with equipment. And at this moment, I'm glad to say that we have already bought our our own equipment, and now in Kazan Physical Technical Institute we can perform these experiments on electrochemical properties measurements. And at this moment I can say that for lithium vanadium phosphate with lithium phosphate we can observe the same value of electrical capacity, but this capacity didn't decrease with increasing the charge rate. It means that this curve with high charge rate should be moved to the right. It's very important from a practical point of view. Then now about ESI investigations. So just let me return back. Here we can see the charge-discharge curve, the discharge curve and discharge curve for electrochemical cell. We suggest that during this process, lithium ions should be removed and then moved back into the structure of this lithium vanadium phosphate. But to prove this fact, we can use electron spin resonance measurements. How we can use ESI measurements? If we look to the chemical formula of the starting compound, we can see that in the case of high quality sample and full stoichiometry, vanadium ions should have the valence state of 3+. In this case, they should have spin 1 and absolutely no ESI signal. During the charge of the electrochemical cell, at the same time, it means that dilation of this cathode material, lithium ions should be removed from the structure. And to save the electroneutrality, vanadium ions can change their valence state from 3+ to 4+. So in this case, they have spin 1/2, and we should observe very good ESI signal. During the discharge of electrochemical cell, during the relithiation process, we can see the opposite process, how vanadium ions change their valence states from 4+ to 3+. This is the theory. What really we can see? For the as-prepared compound, we unfortunately, maybe, we have already observed ESI signal. We suggest that the signal was from vanadium 4+, which was in the as-prepared sample because of non-stoichiometry. And in the composite with carbon, the amount of vanadium 4+ was about 1 or 2%, and in the composite with lithium phosphate, the amount of vanadium 4+ was much higher, about 10%. Then, as I have already told, that during the dilithiation process, vanadium should change their valence state to the 4+, and really we can observe very significant changes in the ESI spectrum, in the intensity of ESI spectrum. And at this moment, I can say that to perform ESI measurements, we really need very low amount of the sample. So we do not need destroy the electrochemical cell. We do not need perform magnetization measurements to check the valence state of vanadium. We can take this very low amount of the sample and then to continue our electrochemical measurements. And so then charge, then discharge of the electrochemical cell, and we perform the relithiation process. And what we observe that the signal from relithiated sample is much lower than the intensity of the signal from as-prepared sample. It means that all vanadium ions go to their initial state, vanadium 3+, and it's very important from an electrochemical point of view. It means that we can use this compound as the potential material for lithium-ion batteries as a cathode material. So here you can see my conclusions, and the main of them is the last, that ESR method allows us to observe the complete reduction of vanadium ions and to prove our electrochemical measurements. So thank you for your attention.
Thanks very much. Questions, please. Uwe, please, your question. Turn on the microphone, please.
Thank you. You hear me, I guess, now? Well,
Yeah.
I switched just in the middle of this lecture. I just came home. I have a question. You used, of course, and that is a method which is used since long times, electrolytical cell for EPR. Have you tried to do measurements in NMR in electrolytical cells, which are in principle a way
you mean
as
NMR
well?
measurements for lithium ions? Yeah, it's in our future plans this year, I think.
Okay. If there are no further questions, then let's thank you, Tatiana. And I would like to also thank all the speakers in this session, and as well as the organizers and the people who provided technical support for the session. So let's give them the round of applause.